The title is maybe a little short compared to exactly what I'm going to talk about, but I thought to put something a bit more global, hence why extreme challenges. And I put that little cartoon there to kind of reflect a little bit of what is happening in Australia. We always hear about climate extremes and high temperatures, droughts, and things like this. So that's the kind of research that I'm interested in. So some of the motivation of the work that I've been doing in the past couple of years is, if you look at these two tweets from the Bureau of Meteorology, it's from January last year, and basically there was a heat wave in Australia. In the western part of New South Wales, the temperatures were reaching like 45 degrees Celsius and above. So typically when people are using extreme value theory, experts are using extreme value theory, is because they want to have answer to questions such as the one I put at the bottom of the slide. So what is the maximum value that a process, so here, for example, the temperature is expected to reach over some region of interest, that could be New South Wales, Australia, etc., within a long time frame. And so if you think at Australia and you look at the tweet on the right-hand side, you see that you can have a lot of monitoring stations. So we collect a lot of data nowadays. The problem is, how do you really analyze and get meaningful information from this high-dimensional spatial data? So one way you can do these things is called through Maxible Processes. So it's a good way to do spatial extremes. And just a little bit of a technical detail, how it's constructed is that you have some replicates, the x's, of a stochastic process, x. It lives into some space, which is, for example, your study region, which would be Australia. And you're looking at the rescaled component-wise maxima. So you take the maxima of your x size, and they are rescaled by two functions that are an and bn. And this is going to converge in distribution to a stochastic process that we call a Maxible process. Now, if you force the margins to be unit Fréchet, so that's heavy-tailed, then you know that the distribution function of your limiting process, of the Maxible process, can be written as exponential minus v function. And that v function is what we call the exponent function. So there is an analytical form. Based on what stochastic process x you take, you will have different exponent functions, which are different ways to express the dependent structure that you're going to have between your extremes. So in that case here, what happens most of the time is that the exponent function is the sum of d terms, and each term is d minus one dimensional CDFs. So you see the problem coming here, where you have a lot of locations in your space, so d is large, and just your exponent function is many terms and high dimensional ones. So how do you do inference for this kind of models? Well, if you were doing full likelihood inference, you need to take the partial derivatives with respect to your d components. So you have your exponential term is going to stay, and then you will have the sum and then a product of all the partial derivative of your exponent function. So this is going in very large numbers.
Hi, Boris. Just excuse me. Time is almost up, and please be more efficient for your presentation. Thanks.
Yeah. Okay. So you have very large numbers here of components. So you have two alternatives to full likelihood. You can do composite likelihoods or Stevenson and Town likelihoods. In my research, what I've been doing is lately combining both methodologies. And if I do this, I can reach 100 dimensions in space. And this is going to take on average 5 to 6 minutes compared to hours or even unfeasible conclusions from other research. And also aggregating data into histograms. So you can use different kind of histograms and do pairwise composite likelihood. And in that case, you can see that in less than an hour, I can also do about 100 dimensions. So that's a quick summary of what I'm doing. Thanks.